Hello and welcome back. Hopefully, the second exam wasn't too overwhelming. And I am here to now present the slides for chapter 10. Now, there are about 48 slides in this chapter, so this will be one that I will be doing in two parts. So I will do the first 24 slides or so today or right now, and then I will record the other half later. But I'll put both of those recordings up probably by Monday. So at this point in the class, we have gone over two of the three types of claims. We've gone over frequency claims in good detail with reliability and validity, construct validity, specifically looking at those with one measured variable. We have also looked at ways of recruiting using randomized or biased methods. We also, in the last chapter, looked at association claims, or what we call correlations. So basically, for the rest of the course, by design, because our final project is based on true experiments, and we've been talking about this as the goal, this is where we will be concentrating. For this module, I am going to go from chapter 10, then skip over chapter 11 to go to chapter 12, and then finally come back to chapter 11. And the reason for that is you will have just turned in your seed article critiques, which involve two independent variables. So we're going to start off with our introduction to simple experiments today, and then we will skip over to factorial designs with at least two IVs. And then we will go back to chapter 11, which is just sort of an extension of chapter 10, and it is pitfalls of IV problems. So when we talk about the validity, right? IV meaning not independent variable, but internal validity. So remember that simple experiments, as we'll talk about, are the only ones, or causal claims are the only ones that internal validity is even considered for. And of course, that means that it is the utmost important, the most important validity. So we are going to look at things that could threaten internal validity. And in chapter 11, because it's not necessary, right, to go into it, after we do factorial designs, we'll come back and talk about the different ways, what we know as the dirty dozen of threats to internal validity. But we'll start with chapter 1, then you'll see, chapter 10, then you'll see chapter 12, and then we'll go back to chapter 11 in this module before the next exam. So, objectives. We are going to distinguish measured from manipulated variables in the study, which we've already sort of practiced earlier on in the course. We'll look at the experiments, and remember we talked about predictor and criterion variables in an association claim or a correlation. So we will refer to these assignments or these variables by their specific name. IV, or independent variable, which is the manipulated variable. Dependent variable, or DV, which is the measured variable. And anything else that could be compromising to this, we would want to control for. So we would call those obviously control variables, and just to make sure that we all know the difference between them. We had a homework assignment where we were using the causal criteria in chapter 8 to analyze an experiment's ability to support a causal claim. Remember that from that, and if you listen to the answer key recording that I gave you, we talked about that correlations still satisfy the first criteria of covariance, but they do not have temporal precedence, and they do not care about independent, internal validity, because you are, it doesn't matter if a third variable, if something else is explaining the relationship between A and B in a correlation. But if you're saying in a causal claim that A causes B, then it can't be anything else, right? So in order for a causal claim to be supported, all three of these criteria must be met. In a correlation, only one, only covariance. Number 4, we will explain why control variables help in an experiment, can help, wow, I'm really off today, can help an experimenter eliminate design confounds. We talked about this idea of random assignment, and we kind of talked about it in terms of internal validity. I put it on a previous quiz, even though we didn't really need to worry about random assignment. But we talked about a random sample for external validity. Here, we're going to talk about random assignment and internal validity, because you want to make sure that these groups are not accidentally unequal on purpose based on the way that you assigned. If you randomly assign, then there's an equal chance that these people will be in either group. And hopefully that eliminates the variability in that sense. We'll get to that. 6, we're going to describe one of, in case random assignment is either not possible or we want to make sure it's more of a controlled trial, then we will do something called matching. I'll explain its role in internal validity establishment and explain situations in which matching actually may be preferred to randomly assigning and why that might be. 7, I will describe how the procedures for independent groups, which we also call between groups, and for within groups experiments are different. I will explain the pros and the cons of each type of design. Number 8, I will identify a post-test only type of design versus a pre-test post-test, and when a researcher like ourselves might use each one. And are they interchangeable? The answer is no, most of the time they're not interchangeable, but we'll get to that. You can see this is a bigger chapter, so I will also explain the difference between concurrent measures and repeated measures designs, which are types of within subjects designs. And I will describe in a within groups or within subjects design why we would need counterbalancing. Now, this should be relatively familiar to you because we use this idea for our first experiment, the Stroop task. It was a within subject, so it was what we call a repeated measures design. And we will talk about why we use counterbalancing. Now, you remember I gave you that phrase to control for order effects. So this is a type of control variable, and we'll explain. I will go into that a little more. For the last 5, I will interrogate construct validity of the measured variable, meaning the DV, dependent variable in an experiment. We will also look at the construct validity of a manipulated variable or our independent variable in an experiment. And I will explain the role of what we call manipulation checks, as well as theory testing in order to be able to establish construct validity. Now, this is not the case for all experiments, but if you feel like maybe the construct validity is lacking, there are a couple of ways to sort of check your variables and check your validity for these potential errors. I will interrogate 2 aspects of external validity for an experiment, which is generalization, in this case to either other populations or to other settings. And then we will finish off with explaining why experimenters usually prioritize internal validity over external validity. Remember, internal validity is the priority of a causal claim, when it is difficult to achieve both, and why external validity, although it may count in this case, a lot of times it's probably the least of the validities, and I will explain that as well. Finally, as we talked about in correlations, normally we use the correlation coefficient R value, and we had those 0.10, 0.30, and 0.50 effect sizes. In a causal claim, we're looking at the difference for at least 2 groups, or the difference between the means. So instead of using an R value to look at the relationship, we're using a D value, which kind of stands for the difference between the groups. And I will talk about statistical significance and why they are important for causal claims or experiments. All right, so what we will do for the first half is looking at simple experiments. I will give you examples of them and how we measure these things. We will look at experimental variables, the manipulated independent, the measured dependent variable, and any sort of control variables that we need. And we will look into the criteria and see why experiments support causal claims. And then in the second half of this lecture, I will talk about independent groups, which we refer to mostly in class as between groups, where subjects are only participating in one condition of the experiment, or within groups designs where everybody does everything, kind of like we did with the Stroop task. So this chapter is simple experiments, which means we're only looking at one independent variable with 2 levels and one dependent measured variable. And then we will interrogate these causal claims for the 4 validities. Because all 4 apply, this is the only one where all 4 apply, and internal validity, which didn't apply in the first 2 claims, is now the priority in the third one. So here's our examples of 2 simple experiments. Number 1, the example is called seeing red. Example 2 would be eating pasta. Yum, for most of you at least. So let's go to the first one called seeing red. So what we see here is a few graphs, and let me go over the background of the experiment before I go over what these graphs say, and hopefully we'll get a little better at reading graphs as we go along as well. So for this experiment, let me give you a little background really quick. In my Psych 1 class, I give them an example of an experiment, simple experiment, for them to figure out what's the IV, what's the DV. And in this example, I use a silly little thing that I wrote that says, that a motivational speaker comes to your class and says that wearing red on the day of the exam causes your brain to be energized and therefore causes you to do better on an exam. So can you design a study, or can you give me the variables where to try to make an experiment to see if this motivational speaker is correct? So in this experiment, the independent variable would be whether or not they wore red on the day of the exam. So half of them were wearing red, half of them are wearing anything but red. And then the DV, of course, would be their exam score, kind of like the studying or not studying example that we went with at the beginning of class. So basically what the conclusion of that experiment is that, of course, wearing red is not going to energize your brain, and the motivational speaker doesn't know what he or she is talking about. But I actually also point out to them that it's not just the fact that whether you wear red or not doesn't energize your brain, but I actually would argue, and I tell them this in class, so I got a chance to after chapter 1, that wearing red may actually cause you to do worse on an exam than to do better. And you're thinking, what? Why? Well, think about the color red. Color red means stop at a stop sign. When you get to a red light, you stop at a signal. And red can sometimes mean danger or caution. You have to pull over to the side of the road when you see a red fire engine or ambulance, right? Things like that. When there's red and blue lights of a police car, you have to pull over, things like that. But red is also something that students, even though you may not be consciously aware of it, are kind of averse to, because if you think about it, what color pen did your teachers use when they graded your papers and you got something wrong? Red. That's right. Yeah, sorry, I didn't give you a chance to think about it before I answered for you, but we'll keep this ball rolling, right? Keep this moving along. So in this instance, based on that idea that the color red may not only not help you, but it may actually hinder your performance because of what I just said, right? Students are used to seeing red marks and being very turned off by that. So here they design an experiment where they didn't want to be too overblown. So instead of, they give you one of those, almost like one of those blue books that you would write answers in. They wanted to see people's ability to correctly unscramble words, which we call anagrams. They thought that it might be too easy to understand if the whole cover of the booklet was a certain color. So instead, they gave everybody a general booklet, but on the very inside cover, in these different colored inks, they wrote the participant's number. So it could be 001 or 126 or 333, whatever it is. And the color of the ink that they wrote your participant number was either in black ink, green ink, or red ink. And they wanted to see if the color of the ink could actually predict who would answer more anagrams or who would answer less anagrams in this case. So the prediction based on everything I just said is that um, black and green would do better on or would solve more anagrams, and red would solve less. And basically, if you look at the first example, the first graph on the top left, you see the number of correct anagrams on average, so the effect of the color red on performance, and you see black, green, and red ink color. Now, the levels of the IV are always going to be on the x-axis, and the DV, which is, again, the measured variable, which is some sort of number, is always going to be on the y-axis. And instead of using a scatter plot, we would use a bar graph, kind of like what we talked about with if one of the variables was categorical in a correlation. So here you see that those who got black ink for their participant number solved about 6 right on average. And I think this was over, about 10 minutes or something like that. About 5.5 were solved in green ink, and you go all the way down to red and you see only on average just under 4.5. So what we can see here, although we don't know if it's statistically significant based on this graph, is that red, people who got the color red for their participant number solved less anagrams in the same amount of time than either green or black ink. Green and black seem to be about the same, between 5.5 and 6. So according to this first example in this first experiment, they got what they predicted pretty much. But it could be argued, and I'm sure you're thinking this as you're listening to this and watching, that maybe writing the color of the ink just for their participant number, that they really didn't even notice it. Maybe it was sort of an unconscious thing. So was that really a bias? Well, of course, they said, well, we could change it and we could see in another study, let's make the entire cover of the booklet, we'll make it a little more obvious. We'll make the color of the booklet a color. So in this case, instead of black, they replaced black with gray. And they had gray, green, and red, as you see on the bottom. There's vocabulary and there's math. So instead of using anagrams again, they were replicating the effect of red, and they wanted to see if they got the same effect with a slightly different subject. So in study 3, and don't ask what happened to study 2, it's not here, but in study 3, they used vocabulary words to see how many they'd get right. And in study 4, it was math problems, and everybody got the same, right? The control was for the same type of math problems or the same vocabulary words. And here we have the booklet cover. The booklet cover was either gray, green, or the color red. Same thing with math. And in study 3 for vocabulary, what you see is, on average, those with the gray booklet cover got about 12 to 12.5 right. Those with the green cover got about 13.5 right. And those with red got less than 10 right, about 9.5 correct. Would this be the same for math? Well, yes. What we see is for gray and green booklet covers, and this is study 4, they got just under 8 correct on average, and the red about 6.5. So in all 3 of these studies, the color red does seem to have an effect, and it's a negative effect on performance. Less anagrams correct in the original study, and in the replication studies for vocabulary and math with the entire cover of the booklet red, they did significantly less, solve significantly less problems in vocabulary and math. So, yep, it would appear, and replication shows this, it would definitely appear that the color red has a negative effect on performance in an academic setting. What about example 2, eating pasta? Really quickly, I'll go back to example 1, and one of the things I wanted to point out, because we do talk about control variables, is the fact that I did say they controlled for the type of vocabulary in math problems, and that they were all the same between all groups. Because when you say that A causes B, in this case, the color red causes you to do worse on assignments. It didn't matter what the assignment was. We had anagrams, we had vocabulary, we had math. And in this case, we would have to control for any of those other factors. So how hard the vocabulary was, I would assume and I would hope that they would control for the skill level of the people taking these tests and things like that. Their proficiency in vocabulary or math or things like that. For the anagrams, people who do anagrams on a regular basis probably shouldn't be in the same group as people that have never done them or hardly ever do them, because otherwise we have a problem with an extraneous variable. All right, eating pasta. So in this case, we talk about in this country there is a problem, and there has been a growing problem with the amount of overweight and obese people, which has almost doubled since 1980. That we've seen. So, a lot of times you've seen documentaries and things like that about how McDonald's and other fast food places introduce the supersize and extra value meals and things like that, and that may have led to this epidemic. And so in this case, the researchers of a study wanted to know if maybe it's the size of the bowl that causes people to take more food because they are told to fill their plates, right? And then they're told to eat everything, or at least as children, they're expected to. So researchers wanted to see, by giving participants either a medium bowl or a large bowl, if on the left, A, how much, as you can see, we have the same in A and B, we have the serving size bowl or serving bowl size, medium or large. And remember that our dependent variable is on the y-axis. So in the first one, A, we see the amount of pasta that they took. So essentially, these people were given either a medium bowl or a large bowl, and they were basically in line like at a cafeteria where you would serve yourself pasta. And they wanted to measure how much pasta was in the bowl in the first part of the experiment. And then once they measured the pasta, then the participants would sit down and eat the pasta, and they wanted to see if people with a large bowl would actually take more pasta and also eat more pasta. So in this example, what we see is a bar graph for each level of the independent variable, whether it's medium or large bowl size. And what you can see from this graph on the left, we can see that those who were given a medium bowl, on average, took about 200 grams of pasta. Whether that's enough to completely fill the bowl, I don't know, because I wasn't there. But that was their average, about 200 grams worth of pasta, and that's the weight. For those with the larger bowl, you see that it's significantly larger. They, on average, served about 350 grams. That's almost double the amount, right, from 200 to 350. It's 1.5 times the amount of pasta. So definitely, according to A, those that had the bigger bowl definitely took more. But would that ultimately mean that they would eat more? Well, we do waste a lot of food in this country. However, we can estimate by how much pasta was left in the bowl, and maybe taking the weight before and the weight after, they could see how many calories were consumed of pasta. So what we see here after, on the right side in B, we still have our medium and large bowl. Those who had a medium bowl ended up taking less pasta, and it looks like they ended up eating less pasta. So in this case, the medium bowl, it looks like on average consumed about 275 calories of pasta, and those with the large bowl consumed about 400 calories, maybe a little more, of pasta. So what we would say for this experiment is, if it was predicted that those with a larger bowl would not only take more pasta, but would also eat more pasta, that's exactly what we found. So this would be about the time that I would ask you guys, when we're talking about control variables, what types of things you might control for. And I would think that you would come up with some pretty clever answers, because you guys are a very brilliant class, and I appreciate that. So I'm giving credit where it's due. And in this case, some of the things we might want to control for was the temperature, because some people will eat, pasta that's nice and warm, but won't touch it if it's cold. How appetizing it is. So if one pasta looks better, tastes better than the other one, that could explain why they may take more or even eat more. Um, so same temperature, same sauce. You don't want one with Alfredo sauce and one with marinara, right? You don't want one with meatballs and one without. The one with meatballs, people may want more of, or if you're vegetarian, you'll definitely stay away from it, or things like that. So the taste, the ingredients, the temperature, everything should be kept the same in this case. The only difference we want in this experiment, right, in the original experiment, experiment 1, the only difference we wanted was the color of the ink, or in the follow-ups, the replications, the color of the booklet cover. In example 2, the only difference we want between the groups is whether or not they had a medium bowl or a large bowl. So let's get back to the basics and give you guys a quick trivia question. What is the main reason that researchers do experiments? Now, we know that for an experiment, we have all 4 validities, but we're trying to be as valid as possible. So we'll rule out A. To generalize to more people would be specifically external validity, and that's really probably the lowest priority of an experiment. To be the most scientific, we're already trying to be as scientific as we can. So the only ones that really work here the best are B, to make causal claims, because that's what we do with experiments, to say one thing causes the other, or D, to collect evidence in the real world. Well, if we're thinking about this like a researcher, right, put on your research hats, we know a lot of times that experiments are done in a fake setting, which doesn't always apply to the real world. So in this case, the best answer is B, to make causal claims, because we want to assess cause and effect. Now, whether or not something works in the real world is usually saved for replication or for later experiments, because at first, and we'll go over this in the last chapter, chapter 14, we are in theory testing mode. And what that means is that we are making sure a theory works first in isolation, where we can control for more variables before we test it out in the real world. First, we want to see if studying helps you to do better. We want to see if the type of bowl causes you to take and eat more pasta, if the color of the ink or the booklet cover causes you to do worse on some sort of scholastic thing like anagrams or vocabulary or math. So in this case, the best answer is B. I know that was a long, roundabout way to say it, but I want to make sure to hammer the point home. So what about variables? In this case, variables tell us what it is that we're either measuring or manipulating or controlling for. So here, remember, we don't have predictor and criterion variables. We have independent and dependent variables, and we have control variables. In an experiment, we have manipulated and measured variables, at least one of each. So remember, in a frequency claim, we have one measured variable, usually a percentage or ratio or things like that. Surveys and polls can tell us that. In a correlation, we have 2 measured variables. One of them may be categorical, or you could have 2 continuous variables. But we don't have any manipulated variables. What makes an experiment is not the bar graph or the effect size D or the type of statistic we use. It is that we have at least one manipulated variable, which we call the independent variable, with at least 2 levels, and one measured variable, which is our outcome variable, whatever the number it is that we're collecting. And Remember in a correlation that a third variable causing a relationship between the first two variables doesn't matter. But here, in this case, if we're saying A causes B, anything else besides A that causes B is a problem. So anything C, D, E, F, or G is a big deal and needs to be eliminated or controlled for. We want to say with relative certainty that A and only A causes B. Studying and only studying causes you to do better on an exam. That the size of the bowl and only the size of the bowl, not the temperature, not how tasty it is, not whether or not there's meat or vegetables in it. We don't want any other thing to manipulate or to be cause of why people take more or less pasta. We only want it to be the size of the bowl, so we control for all those other things. So again, the independent variable is called the manipulated variable, and we usually have conditions or levels of an independent variable. So sometimes they're called conditions, a lot of times they're just called levels. That is the manipulated variable. Usually our levels are some sort of control where there's no manipulation, right? Not studying at all outside of class. And there is a experimental variable, 6 hours a week of studying. But that doesn't necessarily have to have a control variable. In the pasta example, as we just saw, we only have bowl size, which is medium and large. There's really no control. You don't want to give them no bowl, right? It wouldn't work in that experiment. So in a traditional normal experiment, we may see a control and an experimental group, but that doesn't always have to happen. Again, with the ink color, very simple experiment. And I guess you could say black or gray could be a control, but in this case, red is our only real experimental one, and the others, I guess, could serve as controls if you want to think of it that way. The dependent variable, again, is sometimes called the measured variable or the outcome variable because it's the outcome we're trying to get. And a good way to remember this is that the dependent variable or measured variable is whatever number that we're getting out of this. So if we were to go back to that example of studying and your test scores, that, how do we know that somebody did better or worse? The number that we're measuring is the number of questions you got correct on an exam. So that's the number we're looking for. In the anagrams one or the vocabulary or math, it's the number of correct answers. For the pasta, it's the number of grams taken and the number of calories consumed. Whatever number you're measuring is a good way to remember the dependent variable. And you guys should be pretty well versed at this by now. Sorry about that. Looks like I got an email. Maybe it was one of you. So a control variable, again, is any variable that an experimenter holds constant, because the only difference we want between the groups, as we discussed at length, especially in the first experiment, the Stroop task, the only thing we want is between groups that's different is the level of the independent variable. So those that studied versus those that didn't study. Everything else we want to be the same. For the Stroop task, we want everything to be the same except for the groups. So the I task and the N task, right? One were words that had nothing to do with colors, but they had the same first letter, same number of syllables, all blah, 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 blah from that one. They were even in the same order, even though they were randomized in the lists. The order in the list was, between the lists was still the same. The only difference between that group is some of them had words that had to do with colors and the other ones did not. So any variable other than the IV is held constant in this case to control for, right, internal validity is what we call it, the third variable, or an extraneous variable. So let's see now. Why do experiments support causal claims? Well, we have those three criteria that we applied earlier to correlations. We know that it satisfies the first one. Experiments establish covariance, which just means that there is some sort of relationship between A and B. If you're saying that A causes B in this case, then there has to be a relationship between A and B. But in a correlation, we had just pointed out that Temporal precedence is not a thing, because if you are looking at crazy cat person and you measure the number of cats the person owns, or you measure how crazy the person is by some sort of scale, it does not matter which one you do first. You can measure the number of cats first, you can measure their sanity on some sort of standardized test, and it doesn't matter which one you do first, because the relationship could go either way. It doesn't matter if A is related to B or B is related to A, they're both related to each other, so that doesn't matter. In an experiment, though, if you're saying studying causes you to do better on an exam, you cannot give them an exam first and measure their score and then put them into groups of studying or not studying. That makes zero sense. So you have to have temporal precedence in that situation. And of course, well-designed experiments establish what we call internal validity. When you're saying A causes B, you're saying A and only A causes B. So if I go back to our studying example, it is studying and only studying that causes you to do better on an exam than not studying. It's not how much caffeine you had, how much sleep you had, what you ate for breakfast or lunch. It is only whether or not you studied. And so in order to establish internal validity, we hold everything else constant, just like we did in the Stroop task. So here's the 3 causal rules again. We have covariance, asking is there a difference? If both variables are the same, if there's no correlation between them, if there's no relationship between them, then covariance is not established and you can't have internal validity. To say that one thing causes another, they have to have a cause-effect relationship. So covariance works for a correlation, because a correlation means, by definition, they correlate, they have a relationship. But the other two don't work. So for a causal claim, to say that one thing causes another, you need all 3 of them. So we can test it. Studying and exams. Is there a correlation? Is there a covariance, I should say? Yes, because we've seen throughout the years, and you probably have some personal history, that if you study more, you probably do better on an exam, or at least study at all. So yes, we would meet covariance there. Temporal precedence. Again, the IV is manipulated, so it has to come before the DV. I have to give you the size of the bowl before you take pasta. I have to give you the booklet with the cover or the ink on it before you solve the problems that I give you. So in this case, for those claims that we talked about, the studying example and the other 2, the seeing red and the pasta example, we have temporal precedence. You have to give the medium or large size bowl before they take the pasta and you measure it. You have to give them the booklet with the ink or the booklet cover color before they solve the problems. So we do have temporal precedence there. If it was just a correlation, it wouldn't matter. And 3, the most important, is they have to establish internal validity, which means that the taste of the pasta, the temperature of the pasta, how appetizing the pasta looks, all of those things should be held constant for both groups, or all groups, depending on how many there is. In the seeing red, in the first example of the experiment, there were 3 groups, not 2. So we ask the question, are there extraneous variables? In this case, we ask, are there design confounds? And are there selection effects? And of course, if it is a within subject's design, we ask if there are order effects, and that's where counterbalancing comes in. What it may be hard to see on this graph is where the arrow is. We see something called systematic versus unsystematic variance. And in this case, systematic variance is fine, because there's always a chance that even if you randomly assign people into groups, that those groups may just by chance have different levels in them, or just happen to be one group is stronger than the other. But if we don't use random assignment, then it could be, right, if I just were to call on the people who came in first and put them in one group, and those might be the, when we did go to class, those might be the people that were ready to go and potentially study more than the others anyway. And then the people that kind of came in that were kind of straggling, kind of late for class, I put them all in one group based on where they were. Then it could be that before I either give them studying or no studying, the group that came in prepared and ready to go might score higher on an exam overall compared to the other group that comes in late and is maybe less prepared. And in that case, we would have what's called unsystematic variance. So that would mean that the group on the first group to come in, if I made them my studying group, before they ever studied, they might score higher on an exam than the other group. But if we were to select them randomly so that everybody had an equal chance of being in either group, we sort of level the playing field. And if you have an equal chance of being in either group, the variance should be a lot more similar. And if they do vary, that's what we call systematic variance, and that is usually okay. So we'll talk about these 3 and then 9 more in chapter 11, but of course we're going to go through chapter 12 first. Come. There we go. So experiments establish covariance. When we talk about is there a difference, we usually talk about it in terms of a control and experimental group. Independent variables answer the question, compared to what? If I go back to our example of the anti-vaxxers, we say that, based on Jenny McCarthy, saying that her child, her son, was given a vaccine and a little bit after that had started to show the signs of autism. This is her personal experience, right? One of the things we talked about in chapter 2 is personal experience has no comparison group. In this case, it would be a really, really bad idea to try to run something with only one group. Why? Because what do we compare it to? Oh, well, people with Alzheimer's disease have worse memories. Worse memories compared to what? Compared to somebody their own age without Alzheimer's disease, a normal 60 or 70-year-old person that doesn't have memory problems. That's what we would compare it to. If you don't have anything to compare it to, then you don't have covariance and there's no real study. So covariance is really all about the outcome. We have 3 different types of groups. So we talked about control groups and treatment groups, or what we call experimental groups. But we also have one that we call a placebo group. And you might think, well, isn't a placebo the same thing as a control? And no, there are subtle differences. So it would be really good for you to know the difference between them. The treatment group is the treatment group is the treatment group. What that means is I give you studying, I give you a drug, I allow you, I give you no sleep, I give you the red ink or the red booklet cover, right? That's the treatment group. That's the group that gets the manipulation that we're interested in for our experiment. A lot of times for a placebo group, what we have is a group that's getting some sort of caffeine, or treatment group that's getting caffeine or an antidepressant or things like that. So in that case, the placebo group would be a drug or a drink or something that doesn't contain the active ingredient. Why do you think that we wouldn't give somebody, if we're doing a study on caffeine and we give one group a coffee or a soda, that the other group just gets nothing? Because there may be a problem with, or there may be a difference in their score just based on the fact that they drank something. So for a group that gets coffee or soda as a treatment, the placebo group has to give them a decaffeinated or uncaffeinated soda or decaf coffee, because it might be differences due to just the fact that they drank something. When we do mice, when we run studies with mice, and I used to inject my mice with PCP when I was waiting for studies, because we were trying to develop a drug that would reverse the effects of schizophrenia, and PCP basically mimics the effects of schizophrenia in mice. So we would inject some of them with actual PCP, but if we were running a control, we would use a placebo group that got injected with saline or salt water, because it could be that they acted differently just because they got injected. And if you just inject one half of them with PCP and the other half you don't inject at all, the difference could be, right, then you can't control. The difference could be just the fact that they didn't get injected at all. So in order to make it as controlled as possible, we use a placebo group. So one group gets coffee, the other group gets decaf coffee. One group gets soda, the other group gets caffeine-free soda. One group gets injected with PCP, the other group gets injected with salt water, saline, right? So that's a placebo group. An actual control group means that there's no condition or no treatment at all. So in the studying versus no studying example, the studying would be the treatment group. And those that get no studying, they're not doing anything different. They're not receiving a placebo, right? They're not getting a fake decaf coffee. They're not getting a caffeine-free soda. They're not getting saline injection. They're just getting nothing because there's no need for a placebo in those types of experiments. So one group gets told to study. The other group doesn't study at all. There's no manipulation there. That's a true control group. No treatment at all. If it is a drug study or something of a substance, you usually have a placebo group. And could you have a control group in that case? Yeah, maybe, just to see if there's a difference overall, right? So you could have a group that maybe gets a cup of coffee, a placebo group that gets a decaf cup of coffee, and a control group that gets nothing. And then maybe you can see, if you really want to, if you want to spend the time and energy and money, to see if the group that doesn't drink anything is any different from the group that drinks decaf coffee. But that's the difference. A treatment group is always the same. That's the one that gets the manipulation. Placebo group gets the sugar pill or the decaf coffee or the saline injection. And a true control group just gets no treatment at all or no manipulation, like not studying versus studying, or sleeping your normal amount versus interrupting your sleep. So experiments establish temporal precedence. In this case, we're talking about cause and effect, so you have to have the cause before the effect. In this case, you can't, again, give them an exam or an anagram before you give them their booklet. You can't give them an exam before you tell them to study or not study. It doesn't work that way. So you can either study or not study, and then we measure the score of your exam. So cause has to come before effect. The IV or manipulation has to come before the DV. If it's predictor and criterion variable, it doesn't matter which way the relationship goes. It just says that there is a relationship. But temporal precedence in a causal claim, the cause has to come before the effect. The manipulation has to come before the outcome. The IV has to be measured before the DV, or manipulated before the DV is measured. So well-designed experiments also make sure that other than A and B, that nothing else gets in the way. So these are design confounds or selection effects. In this case, looking at this graph, it is a little bit different. We see medium and large bowl as the colors, but if you look at the x-axis at the bottom, it says pasta quality, less appetizing versus more appetizing. In this case, the pasta that was less appetizing was consumed less, about 275 calories, and in the medium bowl, and in the large bowl there was more consumed, over 400 calories. Well, here's the problem. Was it because of the size of the bowl, or was it because of the quality of the pasta? Medium bowl seemed to eat less, but also the pasta quality was less appetizing for the people who had the medium bowl. And the pasta seemed to be more appetizing, whatever that means, for the people who had the large bowl. In this way, we have a confound because we did not control for the quality of the pasta. We don't know if the people in the medium bowl ate less because they had less or because it was less appetizing. We don't know. We don't know if the people who had the large bowl ate more because they took more because it was a larger bowl, or because the pasta itself was more appetizing for some reason. We can't separate these out. And so we can't really know. It's confusing. That's what we call a confound, right? Anything else that has to do with it. So we have to control for that. If the medium and large bowl had the exact same pasta to choose from, and there was not a selection of which one is more or less appetizing because they were both equally appetizing, because maybe it was the same pasta from the same, dish, then we wouldn't have to worry about this. If that's the case and we controlled for the quality of pasta, then we would say that the effects of eating less or more were due to the fact that those that ate less ate from the medium bowl, and those that ate more ate from the large bowl. The other one is selection effects. And that we wanted to make sure, right? One of the other things you want to control for as well is maybe how hungry the participants were. So we want to know that each person in the group had an equal chance of either getting a medium bowl or a large bowl, and that they didn't say, oh, I'm really hungry, so give me the large. This isn't like your choice when you're ordering at McDonald's, right? Or some other establishment. This is that people were randomly assigned and randomly selected to be in either the medium bowl or the large bowl group. So what is a design confound? That's the problem of systematic variability. When things happen systematically, it could be that the people who had the large bowl just happened to be hungrier on average, but they were randomly assigned. So the groups should relatively be about the same variability if they're randomly assigned. That's the idea behind this. We kind of minimize the error. But if something else is causing it, then it's unsystematic, right? So if we don't control for these things or randomly assign, then that's a problem. So potential threats to internal validity. Design confound means another variable accidentally varies systematically along with the IV. So how do we deal with that? We control for those things. In this case, the number of correct anagrams for black, green, and red. We want to make sure that everybody that took this anagram test, shall we say, the anagram experiment, had an equal strength or an equal skill in anagrams. What if the people who were had the black and green ink were already just naturally better at anagrams than the people in red? Well, then that difference wouldn't be because of the color. That difference might just be because those who had a black or green ink booklet were better at anagrams. So one of the things we control for is your anagram level of expertise, maybe, and everybody would have the same average level of expertise of anagrams. That way we can control for that, and this graph would mean what we were intending it to mean, which means those who had the red ink performed worse, but everybody had similar skill. Selection effects. What's a selection effect? Well, let's look at this graph on the left. We can see that there is two groups, treatment as usual and intensive treatment, and see how much they improved. What this study actually looked at was for autism, people on the autism spectrum, giving them treatment as usual or letting them self-select into wanting a more intensive treatment. So here's the problem. Those who choose the more intensive treatment, sure, that could have led to more improvement, but my guess is, and probably your guess, is that it may not just be the intensive treatment at the facility. Those who signed up for more intensive treatment might also be giving more treatment at home and more attention to their child or the person with on the autism spectrum, person with autism, I was going to say. Politically correct, it should be autism spectrum disorder. So we don't know if they are doing more than they're supposed to be doing simply because it's a more intensive treatment. So they may be getting more intensive treatment at the facility, but we also may be getting supplemented at home with even more things that the parents are doing and things like that. Whereas those who are treatment as usual, they just kind of leave it be. So not only would selection be a problem here, but there would be a confound with more help outside of the treatment facility as it is. So in order to avoid these selection effects, we randomly assign, and we could simply flip a coin, or we could just randomly select people to be in group A or group B. All right, if there's 20 people, 10 of you randomly we will assign to be in treatment as usual. That would be our control group, and the other 10 we would give to the intensive treatment group, which would be a little more of a rigorous program. But everything else, right, with those confounds, we want to be the same. So outside of the treatment facility, Please just do what you normally do and don't give any more help or treatment or things like that. And don't bring in an outside person to come to the house. Of course, this day, right now, during this time, wouldn't be a thing, but you get it. So sometimes we're still not sure if random assignment is even enough. Let's say that we wanted to look at IQ levels for exams, right? If we were just to randomly assign, there may be a problem that people in one group, even though it's unsystematic variance, may have higher IQs and may be more astute when it comes to exams or projects or problem solving than people in the other group. So in this case, random assignment may not be enough. What we might want to do is use what we call a matching technique. So a matching technique is where you match people on skill level or IQ level or things like that. And this way we can ensure as equal groups as possible, because that's really what we want when we're looking at this. So if we're looking at, again, problem solving skills or some sort of exam, we're going to have 3 groups and we want to match them as evenly as possible. So here we can see that the person with the highest IQ is in group 3, the next highest IQ is in group 2, and the third highest IQ is now in group 1. Then we take the next 3 highest IQs, and this could be based on some test you gave them at the beginning of class, and they all their IQs are there. So then number 4 goes to group 2, number 5 to group 3, number 6 to group 1. So you're not just giving the highest ones to group 3 and the lowest ones to group 1. You're sort of what we call counterbalancing that. And then finally, if you have 30 people, the last 3 with the lowest IQs, again, 28 is going to group 3, the next lowest IQ is going to group 1, and the lowest IQ is going to group 2. So in these, each group has 10 people in it of the 30 for 3 groups, and the order is counterbalanced between highest and lowest of those 3. And that is what we call matched groups or matching. So the last thing we're going to talk about, those apply to, again, between those of you that did the Stroop task, you did both the N and the I, or the I and N, whichever order. Everybody did every level. So everybody read both lists that participated. In that case, we don't have to randomly assign. I did randomly select 10 people to outside, and I brought them in one at a time. And then they brought another one in and another one in. And so we don't have to worry about assignment for a within group because they're doing everything. But we did have to worry about the order in which they saw the lists, because we don't want what we call order effects. We don't want it to be that the people did better on the N list because they saw it first, or they did worse on the I list because they saw it second, or something like that. That's why we counterbalance. If half of them saw N first and half of them saw I first, then the order in which they saw them could not be a factor. That's how we control for it. So order effects are just be not whether or not they studied, but the fact that they saw the same test 3 times, or it can be something we call a contrast effect. In a within group design, you don't have to worry about random selection or matching or anything like that, or random assignment. But you do have to worry about order effects. So here in this group at the bottom, people are randomly assigned to either interact with their own toddler or interact with a new toddler. So in this experiment, let me explain. researchers wanted to see if oxytocin levels which is a sort of neurotransmitter that's not talked about as much in these classes. Oxytocin is higher for new moms or moms with toddlers when they interact with their own kid as opposed to when they interact with another kid. So why would we want to counterbalance for this and control for it? Well, because if we just look at the top row, maybe we can get them to interact with their own toddler first and then measure their oxytocin, and then maybe half an hour later or so, have them interact with a new toddler and measure oxytocin. Why might there be a problem here? If you're thinking about it, and because I don't have anybody to call on, it's because oxytocin levels may stay high if you're interacting with your own toddler. And so that may contrast or carry over to the new toddler. So when you interact with your own toddler first, when you're interacting with a new toddler after, oxytocin levels may remain high because you interacted with your own kid first, and oxytocin output may continue to be high. Whereas if you interact with a new toddler first, you may not have as much oxytocin, and then when you interact with your own, that oxytocin level can spike right up. So in order to know that it's not just the order in which you saw them, we counterbalance. So half of the people are randomly assigned to interact with their own toddler first and then the new toddler. And the other ones are interacting with the new toddler first and then their own toddler. So the order in which you play with these kids is not affecting your score. When we come back for part 2 of this lecture, we will talk about independent groups, or what we call between groups designs, as well as within groups designs, advantages, disadvantages, pros and cons, and we will interrogate the 4 validities. I will talk to you guys very, very soon.